Today is the wrap-up section of the final examination for the structural mechanics and design. Let me swap to the good note. Okay, so we have 4 topics in the final exam. The first one is the moment of inertia. Let me change the font size. Landscape is better. First one is the moment of inertia, or the I symbol. This one we use to determine the capability of a section. Okay. The higher the moment of inertia is, means the higher the capability of a section to bending moment will become higher. Okay, so we engineer have to. Oops.
Excuse me, we cannot see your screen.
Okay, I forgot to share it. Thank you so much. Share without audio. Oops. Okay. Can you see it now?
Yes.
Okay. The first topic is the moment of inertia. This one tells us how much is the capability of a section to resist moment. Okay. Ability to withstand bending moment. Okay, and as for this bending moment, this one is the major cause of the failure in most beams. Okay, so we design a beam so it can withstand this kind of external force, the bending moment. Then, so we engineers have to be able to roughly calculate this moment of inertia. Roughly is okay, because to calculate detailed moment of inertia of real structural section is quite time consuming, because the shapes of the structural sections typically not in perfectly rectangle. Let me show you the steel table. Okay. For example, the wide flank beam or the H beam, this one. As you can see, this section is not perfectly rectangle. It has some curvature like this. Okay, it has some curvature. So it is also difficult for us to determine this area and also the moment of inertia of this small section. So we can roughly check, but in detail, we might need some calculation software. Okay, but as you can see, these particular parts, the curvature parts, are very small. So even if we calculate using just rectangle one, the final result will be acceptable for the design. Okay, like this. So today I'm going to wrap up you how to calculate this moment of inertia. And okay, ability to withstand bending moment. Because in the calculation, we can calculate the bending state. Okay, bending state. You can use this sigma. Okay, sigma sign corresponding to the bending, and we subscript it by B in order to indicate that this one is the bending. Okay, this bending moment is equal to the bending moment, bending state, sorry, the bending state equal to bending moment multiplied by parameter C divided by this moment of inertia I. Okay, this C is the distance from neutral axis, okay, or centroid to the edge. Typically, let me say to the top or bottom of beam section. Okay, this one is the distance from neutral axis or from the centroid to the top or the bottom of the beam section, and divided by the moment of inertia. This one means the higher the moment of inertia is, the lower the bending state is. So we select the appropriate section that provide this moment of inertia so that we can withstand the we can select the section to withstand the appropriate bending moment. Okay, we from structure analysis. Okay, you have learned how to determine the maximum bending moment in a section, so you can determine this maximum bending moment. And for the section selection, this one we can select from steel table. In every steel tables there will be this value presented. Okay, this I and this C. Sometimes this present as the parameter C. Okay, I divided by C equal to this C, and this C we call the modulus of section. Then once you know this modulus of section, you perform the structural analysis to determine the maximum bending moment that you will use to design. You can determine how much is the actual bending stress in your structure, and then you have only to check whether or not your bending state is within acceptable criteria or not. Okay, so acceptable criteria. Okay, the acceptance criteria of bending state is for working state design. This one is typically 60% of the yield strength. Okay, about 60% of the yield strength of the material. And then you can decide the appropriate section by selecting appropriate whether the moment of inertia and the parameter C, or you can select from steel table directly the modulus of section like this. Then for design, we limit at the limit state is that the bending state is perfectly equal to the acceptable states like this. But it is so dangerous for us designer to design in such scenario because we have no room for our safety. So typically we usually design so that this bending state is lower than the acceptable criteria. Okay, even if the acceptable criteria already include this safety factor, but this one is governed by the laws. So if something we usually design so that we we use our own safety factor criteria. So we design so that these bending states must be smaller than the acceptable one. How much, you may ask? So for me, I will design so that the bending state divided by the acceptable one is about 0.7 to 0.9. Okay, or I utilize about 70% to 90% of this safety of as my own safety factor. Okay, and this one can be negotiable. Okay, if you are the owner of buildings, you can negotiate this value, as this one is the designer's own safety factor. But for this one cannot negotiate. This one is established by the code or laws. So this one cannot be changed. But for the designer choice, we can. Okay, and this, I think for me, 70% to 90% of designer safety factor is acceptable. You have only to check the one who use very small value. For example, a 0.1, 0.2. Like this one is a kind of over design, and we can optimize it. Okay, but I think 7 to 90% is reasonable for me. Okay, and this one is actually is the topics of our final examination. Okay, in the first questions, I will ask you to determine this moment of inertia. Okay, in the first question, I will ask you to determine the moment of inertia of a given section. Then you can get the first parameter in this design formula. Next, problem number 2, I will ask you to determine the internal force of the beam. Okay, beam internal forces. Okay, this one mainly bending moment and shear force. This one. So bending moment is denoted by M, and shear force usually denoted by V. Okay. Actually, there are more than this force. Actually, there is axial force and also the torsion. Okay, but this one is typically very small. So we can neglect it. And also, if even if you design using the bending moment and shear force, most of the time the structure will fail under the bending moment criteria. Okay. In the other words, if you design so that it can pass the bending moment criteria, you can automatically, typically automatically pass the shear force criteria. But anyway, we have to we have to perform the calculation check of both criteria. But for design, we focus on this parameter. If this one pass, so the shear force typically automatically pass. Okay, then you can get the bending moment to put in to this formula to design a beam. Okay, this beam internal force. So in this beam internal force, as the beam is not a point, is a line. So the possibility that the moment and the shear force will not be equal throughout the beam span, this one is very high. So we have no only single formula to calculate this bending moment. So we have to perform a calculation in order to determine the distribution of the bending moment and the shear force throughout the beam. Okay, distribution of moment. Let me specify the bending moment throughout the beam. Okay, this one we call the bending moment diagram. Or BMD. Okay. This one you can see how much the moment is corresponding to any position of your beam. And for the design, we not design in particular point. We typically select the maximum one, and we design the uniform section throughout the beam, as for is convenient for the construction. But sure, you can use non-uniform section to a beam, okay, because in the beam the bending moment distribution is not uniform. So near the support you can use smaller section, but at the middle of the beam you have to use larger section like that. But for typical residential building, we usually simplify it into a uniform section as for the convenience of the construction. Okay, and for that of the shear force, we call shear force diagram, or SFD. Okay, and in the exam, I will ask you to determine those diagrams. Okay, the bending moment diagram and a shear force diagram of a given beam. Then once you can determine the bending moment diagram and the shear force diagram, you can see the distribution of bending moment and shear force throughout your beam. And from that point, you can determine the maximum bending moment and the maximum shear force of your beam in order to put in to this design equation. Okay. This one is my second problem in the exam. And I think these two problems will have the most time consuming. The later question is just concept checks. Okay. Next one is about the load. Okay. This one I will ask you to classify the load. Okay. We have many types of load: the point load, the distributed load, the dead load, live load, so on and so forth. Please memorize it technical terms. Okay, which one is which, so you can easily answer this question. There is no calculation for this problem. Okay, type and load classification. And the last one is the beam state. Okay. Last one is the beam state. Actually, I already described in this part. Okay. So this one we determine how much is the actual state inside our beam. Okay. It's governed by this equation. The bending state equal to the bending moment multiplied by the parameter C divided by the moment of inertia. Or in some time, we can shorten the calculation into this one. Okay, the bending state equal to moment divided by section of modulus. This one is moment of inertia. And this one is the modulus. of section. Then we can, once you determine the maximum bending, we determine the bending moment, you can determine the bending stress. And in design, we use the bending maximum 1 equal to the maximum bending moment divided by this parameter. Let's use C first, multiply by parameter C divided by the moment of inertia I. Okay. Then once you know the maximum bending moment, you can design which section modulus or moment of inertia you would like, you will use to design. For this problem, is not actually a calculation one. If you have a sense, if you can connected the equations, so I can say that no calculation is needed to complete this problem. But if you are not sure about your concept, you can perform the calculation. Okay, you will get the answer also. Okay, so this one is, I'm going to check you this concept, how you understand this equation. Here, how you connect the knowledge of the bending stress and the maximum bending moment. Okay, and we have these 4 problems. Okay, the majority of the points are on the first and the second problem. Okay, let's get into the this one is the wrap up of what I have teach you in the final part. Okay, we have 4 topics. Let's jump to the first one, which is the moment of inertia, how we calculate it. Okay. The moment of inertia, actually, I will not go into the derivation of the formula, but this one is a kind of the moment of the section. Once we have a moment of the section area, once we cut the section into the area, we can determine its moment of the area. So it's sometimes we call the second moment of area. Okay, so actually we have many formula depend on the shape of the section. Okay, like this. But luckily for construction section, material section is typically in rectangle shape. Okay, so we have only to memorize this formula only. It's very rare for us to encounter triangle shape or other shapes. Okay, typically structural steel are in rectangle shape. Okay, but sometimes circular shape is also presented. Okay, but this one I'm not memorized also. I just open a textbook in order to check the formula. But for this one, you have I think it's better for you to memorize. It will help you to image the capacity of the beam a lot. Okay, the moment of inertia equal to BH cube divided by 12. Depending the B and the H, B is the base and H is the height. It depends on the axis that you have looking at. Okay, if in this case if we have a look at x direction, x axis, so the moment of inertia over x axis equal to the base. Okay, this B multiplied by this S cube divided by 12. Okay, but however, if you have a look at this y-axis, you have to flip your look. So this one will be your base. Okay, so your base will be this h, and this b will be your height, respective to this y-axis. So this parameter swapped. Okay, please be careful. For x direction equal to bh cubed divided by 12, and for y direction equal to hb cubed divided by 12. Okay, this one. But I already give you this. And I cannot remember, but I think I already give you this formula. Okay, I present this formula in our exam. But for this one, I'm not quite sure. But maybe only this one, I think. Okay, but please be careful that this one is not universal. It depends on the axis. Okay, if you if you change the axis, you have to change this parameter, swap this b and this h also. But please just memorize that it's a base multiplied by the height cube divided by 12, and it's fine. It will be fine. Okay. Okay. Let back to our okay. Let back to our paper, and this one we for I. Okay, I of how to say simple shape. We use formula. Okay, such as I equal to b h cubed divided by 12 for rectangular shape. Okay. For example, if I have, for example, if I have a beam, a simple beam, and the contractor asks me whether this section this solid section one has the dimension of let's say 30 centimeter. Okay, 30 centimeter by 10 centimeter. Okay, and the other section is let's say 30 centimeter by 15 centimeter. Okay. But it's not to scale, so let me expand it a little bit. Okay, if contractor asks me beam A or beam B, which one is which one? Oh, but this one is not good example. So let me make it the same. Let's say 10. Okay. I would like to make it sectional area the same as the material cost would be the same. Okay, if I use different sectional area, so the price of the material will not be the same, and it will not be perfectly comparable, because we have to consider about the price. But for this one, is sectional area is the same, so we can compare it all by the section only. Okay, this one. So for the beam A, and this one is where we apply the load. Okay. So let's check the moment of inertia of the beam one first. Okay, so x equal to bh cubed divided by 12. So in this case, the b is the base, right? Because now we considering in x direction. Okay. This one is x direction, this one is y direction. Okay. In some textbooks, we will encounter XC direction or YC direction, depend on how you have a look in along the beam longitudinal direction. Okay. So this one is 10. Okay. And the h is the height of the section, so it will be 30. Then 30 cube divided by 12. Then you can hit your calculator. Then 10 multiplied by 30 cube divided by 12. 22500. And please don't forget the unit. Okay, this one is very important. So this unit is in centimeter. This one is also centimeter. So centimeter multiplied by centimeter cube. The grand unit will be centimeter power by 4. Like this. And this one is moment of inertia of this beam against the load come from y direction. Okay, the load come from y direction. If the load come from y direction, we need to use the moment of inertia in x direction. Okay, because the x axis is the one withstand the load from the y direction. In the other word, in y-axis, we can use it to support the lateral force, in which this beam is not withstand this kind of load. So we determine only x-axis is okay. Next one is the beam B. So Ix equal to BH cube divided by 12 also. In this case, this B is 30 centimeter. And the h is 10 centimeter cube divided by 12. And then we can 30 multiplied by 10 cube divided by 12, 2500, like this. In the other word, this beam A is about 10 times, not 10 times, 9 times greater in response to the load from y direction. Okay. Compared to beam A, compared to beam B, like this. So in this case, we have a better use beam A to withstand the load in y direction. But if you would like to withstand the load from x direction, okay, point into the paper or point outward from the paper, this beam section will be more appropriate. Okay, depend on the direction of the load. Okay. Then this one is for simple shape, but in reality, this simple shape presented only in reinforced concrete structure, I think. For structural steel, this shape is typically not be used because it will be very heavy. So we use composite shape. Okay. Moment of let me say the composite shape. Okay, the composite shapes. Composite shapes is the shape composed of many simple sections. For example, Y-fang beam. Okay, or H-beam. Okay, T-bar, tube, so on and so forth. These are composite shapes that we cannot simply use the formula to determine the moment of inertia of the section. And this one will be our final exam. Okay, so we can say that the summation of the representative moment of inertia in x direction must we will use this formula has the name. Let me recall. Okay, we call parallel axis theorem. Okay, so the moment of inertia in x-axis must be equal to the summation of small moment of inertia of any simple piece in x direction, okay, plus summation of the area, okay, small area multiplied by dy cube, like this. Okay. Si is the moment of inertia of component. Okay, a simple one. This one is the area of component. And this dy is the distance from the section centroid to the component centroid. Okay, distance from the section centroid to the component centroid. And as you can see, we need these all parameter in order to calculate the overall moment of inertia of a section. Okay, in y-axis is swap. Okay, so summation of small moment of inertia in y direction plus summation of sectional area multiplied by dx square. Okay, like this. And the parameter has the same. Okay, that just swap the axis. Yeah, this one is parallel axis theorem that we can use to determine the moment of inertia of any composite section. And as you can see, this composed of a very simple calculation. We can calculate it. We can calculate it easily using a simple equation. Let's have a look at an example. I will use the real one to show you. Okay. I think there are many of these H-beam in the class material, so I will use other section. Okay. Let's use this cut beam. Okay. So so easy for us. Okay. Let's calculate this cut beam. So I will. A moment. Okay. This one we will check the calculation. We will check that. Let's say this section. Okay. Cut beam 75 by 100. We will check that is it true that the moment of inertia of this section in x direction equal to 51.7 and in y direction equal to 75.3. Okay, let's check this one. So to do this, we may need to use a table because it will be easy for you to track what you are using in the calculation. Okay, so the table start with the component. Okay, the sectional area. Please always identify the unit. Okay, so in this case, I will use exactly as the table give me. All dimensions are in millimeter, so I will calculate the sectional area in square millimeter. Okay, and then I will convert it to centimeter cube later. But let's say I use centimeter directly, so this one will be square centimeter. Okay, the sectional area, the moment of inertia in x direction, this one also in centimeter I will use. Okay, and dy. Okay, distance from the centroid of the shape to the centroid of the component. This one I will also use centimeter. And then a dy square. Okay, this one will be in square centimeter power by 4. Okay, then again for the y direction, I1 cm4 dx cm and a dx square cm power by 4. Okay, this table I already provide to you in the exam sheet, so you no need to draw this one again. Okay. Then let's determine this section 25 by 100. I will draw this one again for clarity. Okay. Then let's check this table. So the width is this y and the height is this h. So we check in the table. Okay, this h 47 millimeter and b is 100 millimeter. So 47 74, sorry. This one is 74 millimeter. So this one is 7.4 centimeter. And this h is, oops, sorry, I have swapped. This one is 100. 100 millimeter or in centimeter. And this one is 74 millimeter or 7.4 centimeter. Okay, from this table. And then we need the thickness of the component. So T1 is the thickness of the web. Okay, so thickness of the web here is 6 millimeter. So one we know that this one is 6 millimeter or 0.6 centimeter. The last one is this one, the thickness of the web. Okay, thickness of the web is denoted by T2. So in this case, T2 of this section equal to 9 millimeter. Then we put in 9 millimeter or 0.9 centimeter to this one. And then we have the dimension of this beam. But as you can see that in the formula, we need the distance from the centroid of the component to the centroid of the whole shape. So you have two choices. Okay, first one, you determine the centroid of the shape by yourself. We already done it in the midterm exam. Okay, I will not going to in detail for this one, but and the second one is you determine it from the steel table. For 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 unsymmetric shape, we can get the centroid of the shape from the table directly. Okay, as you can see. A moment. Okay. As you can see, this shape is symmetric in y direction, so we can say that the centroid of this shape is in y-axis. Okay, but for x-axis, it must be a little bit upper from the center of the shape. Okay, so we have this one. The distance from the top to the centroid of the shapes. Okay, this one so is denoted as the center of gravity, this Cx. Then we can determine this one is 1.5 centimeter. Okay, so now I can say that the center of the gravity of this shape is in y-axis. Okay, in y-axis, and from in x-axis, sorry, and for y-axis it has distance. Let's say the distance is 1.55 centimeter. Okay, like this. And okay, we are good to go. Now we know the center of the gravity of this shape already. Okay. At this point, who had any question or how we can read this steel table? Okay, if there is no, let's continue. Then we separate the shape into components. Okay. So the easiest way is to separate like this. This one is our first component. And this one is our second component. Okay. Doing this way is just rectangle and it has two pieces. It's easy for me to do this one. But if you don't want, you can do other way. Okay. For example, this one is your shape number 1. This one is your component number 2. And this one is your component number 3. This way also okay. You will get the same moment of inertia. Okay. But you will end up with 3 pieces. Okay. So for me, I will use this way. This one is my first component and this one is my second component. Okay, I will neglect this curvature. Okay, so my calculation will end up with a little bit smaller moment of inertia as we lost some area due to this neglection. Then let's start with the first component 1. Okay. Component 1, we have the width of 10 centimeter, the thickness of 0.9 centimeter, and its center of gravity. Okay. Let from here to here, we already know this one is 1.55 centimeter. I think I draw too small picture. Okay, but maybe okay. Okay, then we can start the calculation. Starting from this area. Okay, this area equal to 10 multiplied by 0.9 equal to 9. Okay, the unit is square centimeter. Then moment of inertia in x direction, x-axis. Okay, so in x-axis we look at this direction. So this one will be your base, and this one will be your height. So this one equal to BH cube divided by 12. So the B base is 10 centimeter. H is 0.9 centimeter cube divided by 12. Then hit the calculator. 10 0.9 cube divided by 12. One is 0.61. Okay, about 0.607. 0.61. Then divide the distance from the component centroid to the shape centroid. So this divide would be this one. Okay, divide. Now we know that overall length is 1.15, but this centroid is at the middle of this shape, right? So this divide must be 1.55 and minus by the half of the thickness of this beam, of this component, sorry. So we know that this distance equal to 0.9 divided by 2 centimeter. Okay, then we can know the divide. Okay, I will write in full calculation here first. So in this one, divide plus 0.9, dy plus 0.9 divided by 2 must be equal to 1.55. Okay. Divide plus 0.9 divided by 2, so it will be this distance, which is equal to this one, and this one is 1.55 centimeter. Here, then divide equal to 1.55 minus 0.9 divided by 2. Then we get dy 1.55 minus 0.9 divided by 2, so 1.1. Oh, okay, 1.1 centimeter. Then we get this dy. Then a dy is just the calculation, so 9 1.1 cube, square. 9 multiply 1.1 square. This one is 10.89. 10.89. Again, we do it for the IY. Okay. So in Y direction, we switch our point of view to here. So this one will be your base, and this one will be your height. Okay. IY equal to BH cube divided by 12. So your base is 0.9. Your height is 100 cube divided by 12. Okay, 0.9 multiply 100 cube divided by 12. 75,000. Okay, 75,000. Oops, sorry. This one is not 100. This one is 10. Just 10. Just 75. 75 for Y direction. Okay, and then dx. The centroid of this component is at the middle of the component. So the dx must become 0 because this one is symmetric in Y direction. Okay. This one is symmetric in Y direction. So this dx must be equal to just 0. Okay. No distance from the centroid of this one in x direction to the centroid of the shape. Okay, because this one you can have an image that this one is symmetric in Y direction. So there is no misalignment of this centroid of the component to the centroid of the shape. So if x dx equal to 0, if this equal to 0, this whole term must be equal to 0 automatically, so I will not perform any calculation. Then we get the first one of our calculation. Then this one is finished. Okay, then we move to the component number 2. Okay, component number 2 is this one. Okay, I will draw the upper one as for the reference of the centroid. Okay, and we have the centroid of the overall piece of the section and the centroid of the component itself. Okay, for this one, I will write down the dimension. This one is 74, I think. Okay, 7.4 centimeter. Okay, this thickness is 0.9 centimeter. 0.9 centimeter. This thickness is 0.6 centimeter. And from the top corner to the centroid of overall shape, this one is 1.55 centimeter. Okay, like this. Then real quick, I will calculate this. I will determine this one. Okay, so this one equal to 7.4 minus 0.9. This one equal to 7.4 minus 0.9. 6.5 centimeter. Okay. Then we can calculate the area. Okay. This one equal to 0.6 multiplied by 6.5. 0.6 multiplied by 6.5. 3.9. 3.9. Then the moment of inertia in x direction equal to bh cubed divided by 12. So this one in x direction, so we have to look in this direction. So this one will be your base and this one will be your height. So this one is 0.6 multiplied by 6.5 cubed divided by 12. 0.6 multiplied by 6.5 cubed divided by 12. 13.73. Okay, 13.73. Next is dy. Okay. So for dy, we know that the centroid of this component must be at the middle of this component, right? So this one must be 6.5 divided by 2. Okay. 6.5 divided by 2. But we need dy. dy is the distance between this point to this point. Okay, so we need to the easiest way for me is to determine this distance first. Okay. The green one is from the top to the centroid of the component. Okay, this green one must be equal to the thickness. Okay. This 0.9 centimeter plus half of this half of the width of the height of the component. So this green one equal to 0.9 plus 6.5 divided by 2. Okay, this green one must be equal to 4.15. Now, then we divide is equal to the green one. Okay, this divide must be equal to the green one minus the black one. Okay, the black one minus the green one must be equal to this divide. Okay, so This one, let me name the green one minus the black one must be equal to the dy. Okay, so the dy equal to the green one. I already calculate here 4.15 minus the black one 1.55. This one equal to 2.6. Okay, 2.6. Then a dy, this one equal to a dy 2.6 square. $76.36. Okay. Next, the I1. I1 equal to BH cubed divided by 12. So this time we look at this direction. So this one will be your base and this one will be your height. Okay. So base is 6.5. The height is 0.6 cube divided by 12. So 6.5 multiplied 0.6 cube divided by 12. This one is just 0.12. Okay. And again, this shape is symmetric in y direction, so there is no difference in the x. Okay. So let's put 0 here. Then we can find out the summation of the parameter we need to know. Recall, we need to know the summation of moment of inertia in x and in y direction, and we need summation of a dy square and summation of a dx square. Okay, so in this one, we need summation of moment in x direction. Let me use this bar. Summation of ix bar equal to 0.61 plus 13.73, 14.34. This dy we no need. We need again is the a dy. Okay, sigma a dy square. Okay, this one equal to 10.89 plus 26.36. 37.25. Okay, and again I want 75 plus 0.12. This one is 75.12. Oh, let's get to what summation of I bar equal to 75.12. dx we no need, and the adx square, this one is 0 because all terms are 0. Then we can summarize. Okay. Ix equal to sigma I bar x plus sigma a dy square. So sigma ix square is 14.34. Okay, plus a dy square 37.25. This one about 14.34 plus 37.25. 51.59. The unit is centimeter power by 4. And for Iy equal to sigma I y bar plus sigma a dx square. Okay, Iy bar is 75.12 plus a dx square is just 0. Okay, so this one is 75.12 centimeter power by 4. Okay, let's check. Ix in the table 51.7. Our calculation is 51.59 acceptable. And for moment of inertia in y direction 75.3. Our calculation is 75.12. Okay, acceptable. As I said, this one will be smaller than the table because we neglect the curvature part of the steel. Okay, like this is the one we use to determine the moment of inertia of the section. Okay. And from this number, we can say that this beam has more capability to withstand the load in y direction greater than the x direction, as the moment of inertia in x direction is smaller than that of y direction. Okay, please be familiar with this kind of calculation. Okay, as for this calculation, in the exam, I give you this formula already. I give you also this bx cube divided 12 already, and I also provided you this table already. Okay, so you just have only to separate the section into components and then perform the calculation. As for this one, who has any questions or any concern ครับ Okay, if there is no, let's have a short break for 5 minutes, and then in 11 o'clock, 13 minutes, I will continue the beam internal force. let's continue ครับ so we can have our lunch on time. Next is the beam internal forces. Okay. Beam internal forces. Okay, for any beam, if we cut the beam, if we cut the beam imaginarily, then we will find out that there will be internal forces in the beam. Okay. This one including the axial force, okay, typically N, axial force. Okay, the shear force, B. And the bending moment, M. Okay, and these internal forces are the one generate the bending, generate stresses in your structure. Okay, so it is our task to determine these components. But as I said to you, the axial force typically very small. Okay, the main force is the bending moment and the shear force. So in this case, we are going to determine only the shear force and the bending moment. Okay, for axial force, we typically neglected it. Then we have the method to determine the distribution of the shear force and bending moment in a beam. Yeah, a moment. Okay. First, we will cut the beam this way, and then once we cut the beam, we can analyze it like a rigid body. Okay, you have the support. You can detach the beam from the support and represent it by reaction, and then you can determine it as a rigid body. Okay, as a rigid body. So then we continue cut the beam, and then we can get the distribution of the forces. But for this one, as you can see, we can cut anywhere. Okay, so we have to select the place where we cut the beam appropriately. Usually at the point load, if there is point load, you cut there. If there is distributed load, you cut from the beginning and at the end, like that. Okay, cut where is the load. Okay, if the point load, and I will take a note here. Point of cut. Okay, first one at the point load. Okay, or concentrated load. Or concentrated load. Or second one, start and the end, or distributed load. Okay, start or the end of the distributed load. And number 3, at the support. Okay, at the support. These 3 points are where we are going to cut. Okay, for example, if I have this beam, okay, I have point load P1 and point load P2 like this. For this one, we have to cut this one first and this one second. Okay. If I have only one point load, P1, I have only to cut one time this part. Okay. And when we cut, we can have 1, 2, and 3 member to work with. This one we have 2 member to work with. And if I have a uniform load, okay, like this. So I firstly have to cut here. Second have to cut here. Okay, 2 times. And if there is only distributed load like this, you have to cut anywhere, okay, just one time. Okay, this one is special case. Anywhere, okay, just one time. And if you have a combined load, you can use the same principle. Okay. For example, we have distributed load over here and we have point load there. So first time you cut here, second one here, and third time here. Then you will have 4 pieces of beam to work with. Okay, so on and so forth. We can do like this. And when we cut, we will assume that the cutting length is nearly reach the load. So the load will not be presented at the cutting point. Let's say like this.